All right, I believe we are now live. So, welcome back to session number 7, but miniature number 6. So, today we are going to be exploring a miniature about odd distances between pairs of points on the plane. So, the main claim in this miniature is the following: there are apparently no 4 points in the plane such that the distance between each pair is an odd integer. And one way of, well, this does sound like a somewhat ad hoc statement, a really niche fact. And it's not clear how you go about proving something like this, at least not off the top of my head. Maybe geometry ninjas have some tricks up their sleeves that would be considered standard in the business. But when I see something like this, I'm pretty clueless upfront. So I would, if I didn't have the spoiler in the statement, I would probably be trying to come up with examples. So in fact, the statement kind of prompted the following variations. So since we are talking about parities and we've just come off from a long discussion about parities in the last couple of sessions, as it seemed to be natural to ask, what about if you flip the question and say, are there 4 points in the plane such that the distance between each pair is an even integer? Can we answer? So at this point, this is not addressed in the miniature. So as far as we are concerned, open problem. So what can we say about this? I mean, at least for 3 points, and maybe there's just like a little square sitting on the screen. With 3 points, you probably already start thinking about Pythagorean triplets or something like that. What would you say? Maybe let's just take a minute to think about whether the answer to this question is yes or no. All right, so we believe it's yes. And what would be an example of 4 points in the plane where the pairwise distances are all even integers? Okay, 6, 8, 10 in a triangle. So if you have, for example, yeah, and then you kind of reflect that about the axis. And I'm not sure if that's an example of, yes, that would be a Pythagorean triplet. So that's a right angle. That's a right angled triangle with edge lengths 6, 8, and 10 would be the hypotenuse. And you reflect it about the diagonal to get a square like this. And so the diagonal lengths will end up being the two hypotenuse sides. So that would be 10 units. And the side lengths of the square would be 6 and 8, right? So yeah, any Pythagorean triplet which has like the base numbers being even, the side lengths being even, would work. And in fact, I was curious about how many there are. So the Wolfram page on Pythagorean triplets lists the first few, like up to 100 or so. And it's just eyeballing it to see what fraction of Pythagorean triplets have all the side lengths even. And there didn't seem to be that many, but also not that few. So that's a seriously imprecise statement. But and I don't know if anyone's looked at the density of all even triplets amongst all of them. But that felt like a fun aside to try. Okay, so as far as even integers go, it seems like we have some luck in this combinations that work. You could push this in a couple of different directions. One is to say, well, could you try your luck with more points? We've already had a bit of a spoiler where we know that you cannot do it with 4 points and odd distances. Of course, 3 points and odd distances are okay because you could start with an equilateral triangle or something like that and scale it up. So 3 points and odd integers are fine. 4 points and odd distances are not feasible, and we'll see why in just a bit. 4 points and even distances are feasible. So you could try and push your luck and see, could you get more points which have pairwise even distances? And that's something I haven't thought about. So I'm going to throw that in as a discussion prompt for, offline uh, uh, for offline thinking. But I did wonder about a more relaxed version of this question where we ask ourselves, well, how many points can you accommodate on a plane so that the pairwise distances are at least integral? So we don't have any fractional or irrational or funny distances like that. So that's, well, I mean, I think that's an interesting natural generalization. So it turns out that at least there is a finite bound in the sense that you can't just have, you cannot, for example, say, well, give me endpoints whose pairwise distances are all integers, and that you can actually come up with such configurations for any n. That's not going to happen. So beyond a point, it turns out that, well, you start collecting points while trying to maintain that their pairwise distances happen to be integral. And maybe integral is not the right word. I should have just said integers. The pairwise distances are all integers. And then, well, when you bring in a new point, you have to be careful about ensuring that the new entrant has integer distances to all the existing points. And basically, no matter what process you follow, at some point, you're just going to get stuck. So there is a theorem which basically says that, well, okay, so I don't know if this is an equivalent statement, but in an infinite collection of points, if you have that all pairwise distances are integers, the only way this can happen is if all those points are on a line. So you cannot have an infinite collection of non-collinear points which have pairwise integer distances. And this theorem is apparently attributed to Erdős and Anning from a while ago, and it has a very cute counting style proof. And what I'm going to do is maybe walk through that just to build some intuition about the fact that there is a certain kind of infeasibility that comes in beyond a point when you start demanding integer distances. But because that's not the topic of the miniature, I will come back to that after making sure that we've gone through the proof that is in fact in the book, which goes back to the question of showing that there are no 4 points in the plane such that the distance between each pair is an odd integer. So the way we are going to do this is just a little bit of magic in a short computation. So the proof is by contradiction. We start by assuming that there are 4 points whose pairwise distances are odd. And without loss of generality, just put one of them at 0. So 0 on your coordinate plane. You can do this just by sort of an appropriate translation, so that's fine. And so the 3 remaining points, I'm denoting A, B, and C. So we have 1 point at 0 and these 3 other points. And the claim is that these distances, so the first 3 are just the distances between 0 and the points A, B, and C. And the others are the pairwise distances formed by the triangle ABC. The claim is that, well, all of these happen to be odd integers somehow. And it'll just be a useful fact that if you square up these odd integers, then they all turn out to be congruent to 1 mod 8, which is to say that they all leave a remainder of 1 when divided by 8. And I'm not sure about you, maybe this is just blindingly obvious to some, but I just wanted to be sure that this is indeed the case. So in general, let's just confirm that if you have an odd number, then its square always leaves a remainder of 1 mod 8. So if you have an odd number, then you expand out to k plus 1, and sure enough, you get whatever you get. This is 4k squared plus 4k plus 1, just by simplification of terms. So we pull the 4 out, and at this point, this is kind of promising. We do have that it's 1 mod 4 based on just this form. Now we break this down a little bit further and write k squared plus k as k times k plus 1. And between 2 consecutive integers, we know that at least one of those 2, in fact, exactly one of those 2 must be even. So either the k or the k plus 1 is going to be even. So that gives you the form that you want. So this is 8 times something plus 1. Is this reasonable? Just to get a sanity check, could you give me a +1 in the chat if we are good so far in terms of the setup? and this little claim about the 1 mod 8. All right, super, thanks. Okay, so now we go back to doing magic. It's probably not so much magic yet, but we will see that we're going to do a computation that's pretty funky. So let's look at these inner products here. This is, I think, is this the thing that's called the, is this called the cosine formula, whatever this is called. The if you line up these inner products, A, B, B, C, and AC, then what do we have on the right-hand side? Well, we have these terms which are all odd. So we have the sum, well, so let's look at the first, just look at the first one maybe. So A square plus B square minus A minus B square. Okay, so I'm not emphasizing the norms and the distances. Hopefully the notation makes that clear. So we have a sum of two numbers that's odd to begin with. So those two numbers sum up to an even number from which we're subtracting again an odd number. So that leaves us again with an odd number. So I hope that these three claims here are okay. Sorry, I'm just going to request a little more exercise and give me a +1 if I can move on. All right, super. So mod 8, that's just because, okay, so the term, okay, so that's a good point. So each of those individual terms are 1 mod 8, right? And so I guess, I don't know why I was emphasizing that the, okay, I don't know, I don't know why I was emphasizing that when that the numbers are odd. That's not what I wanted to say. I wanted to say that each of these individual numbers that go into these operations are 1 mod 8. And therefore, when, okay, if I sum two numbers which are multiples of 8, then the resulting number is still a multiple of 8, right? Because, well, we just divide evenly into both of them. Does that make sense? It's the same idea when you go when you have a common remainder. Let me just take a minute to confirm that I'm making sense when I say that. If anybody wants to help me out in the chat, let me know. Oh, okay. Do you mean you're not suspicious about the arithmetic being claimed here, but you're wondering why are we going mod 8 instead of something else? Okay, that is something that will hopefully get addressed as we move on. But okay, I just wanted to make sure that the mechanics of the claim that's being made here is okay. I just realized that I went off on this tangent about claiming that these numbers are odd, which is not really relevant. It would have been if I could have said that they're odd squares, but I think this is a lot more direct just based on the fact that the numbers involved here are already 1 mod 8. So I think we are good on that. Why didn't we take mod 2 or mod 4? Well, I just don't know if going mod 2 and mod 4 would be enough for the computation that we have in mind. So maybe let's look at the contradiction that we're about to get. Let's just remember that this is a proof by contradiction. And we'll probably see that the mod 8 turns out to be really useful. Okay, so since it's basically a computation, it's just something that checks out. So let's take a look at what we want to do with these numbers. So let me dump all of this in all of these terms in this matrix. So we have these inner products laid out as they are in this 3 by 3 matrix. And okay, so what we have here is, well, if we were to take this matrix and we went mod 8, then we get the matrix that we get to the right. I'm just recording, I'm recording this the entries of this matrix, but by going mod 8. Okay, and this matrix that we have on the left, I think we are back to talking about matrices being full rank. So maybe does somebody want to volunteer why the matrix that we have on the left has rank 3? Oh, 2 raised to rank, where rank is 3. Okay, I'm not completely sure if I follow that line of argument. I was wondering if maybe there is a more sort of okay, maybe we can take the echelon form. Okay, I don't know if okay, so I didn't put the calculation on the slides, but it turns out that this, okay, the form that we have on the right, which is where we are writing these congruences. So basically we have that 2 times this matrix here is congruent to the matrix that we have on the right, mod 8. Now you can take this matrix here, the 2, 1, 1, 1, 2, 1, 1, 1, 2 matrix, and just compute its determinant, which I think is maybe not even hard to do by hand if you just stare at it. But it just turns out that if you compute the determinant, it turns out to be 4. Okay. And it's a little bit of modular arithmetic. So it's a little bit of modular arithmetic to confirm that the determinant of the matrix on the left is congruent to 4 mod 8, which is to say that if entry-wise you are congruent in a certain manner to mod 8, then those congruences will just sort of carry through because congruences are preserved over normal arithmetic operations. Okay. So basically, the claim here is that the determinant of 2 times b is congruent to 4 mod 8, which means that the determinant of 2 times b is non-zero, which means that the determinant of b is non-zero. Okay, so you could probably do it in a more direct way, but this is the explanation that's straight from the book, and that's, I think, I don't know if this is the only place where the mod 8 turns out to be useful. And notice that here we get determinant of this matrix here, the 2, 1, 1, 1, 2, 1, 1, 1, 2 matrix. That turns out to be 4. So the determinant of 2b being congruent to 4 mod 8 helps us reason that the determinant of 2b is non-zero. I'm not sure if, for example, at this point, if we had gone, so because the value of this matrix is 4, if we were 4 mod 4, for example, then we would not have been able to conclude that the determinant is non-zero. So this is to answer your previous question about why are we going mod 8. It turns out to be useful in being able to say that the determinant of this matrix being congruent to 4 mod 8 ensures that our determinant must have a non-zero value. Okay. There are a couple of suggestions in the chat saying that, well, because the matrix on the left has a certain form, we know that it's positive semi-definite, which may not be enough to argue full rank. We can probably argue that it's positive definite, which is an approach that we used to show that another matrix was full rank in one of the previous miniatures. So that's certainly an approach to showing that something is full rank. The echelon form will be similar to the identity matrix. So I have a feeling that doing echelon forms with the terms that we have on the left might end up being messy, but it's probably something that's worth checking out and seeing if it works. Um, but basically seeing that each of these terms is one mod 8, each of the non-diagonal terms is one mod 8. This is the part, like, basically demonstrating full rank is the part where that turned out to be useful. I want to now get this contradiction by simultaneously showing that this matrix is not full rank and has rank 2, and that will give us the contradiction that we are after. But before that, is this non-zero determinant going via congruences reasonably convincing? The one part that I have not, I mean, I think I really should have put this on the slides, but anyway, I think I'll make that addendum post facto. The one thing that does require like an observation is the fact that when you have the value of the determinant of this matrix on the right-hand side, which is basically capturing entry-wise congruences mod 8, then the determinant of the matrix on the left is also congruent to the determinant of the matrix on the right, mod 8. And like I said, that's just because modular arithmetic operations go through with, they're kind of preserved as you do these. So the determinant is the sum of products. And if you look at it that way, just look at the expansion. I think if you just stare at the expressions on both sides, so this is something that I've worked out by hand, and it's a parenthetical remark in the miniature. But that's something that does require a bit of staring and confirmation. But in terms of the spirit of the argument, hopefully this is not too bad. Joel's asking if we should have worked over F8. Now let me just make, so F8 as a field, yeah, if we could have interpreted the entries as being in F8. It's just that I'm not sure with Euclidean distances, the elements of F8, would they be enough to capture? Because these could be any odd distances. So I'm just wondering. So 8 is not a prime, but it's a prime power. So I was wondering if we could still make this work, but okay, I'm just not sure if F8 naturally, or if basically that's a different way of saying that things collapse, but okay. So anyway, that's okay. There's a full rank argument here. That's one arm of the contradiction, and that's being pushed by a non-zero determinant argument, which in turn slickly relies on the fact that this matrix is congruent to a matrix whose determinant is 4. Okay. So 4 mod 8 is non-zero. The actual value of the determinant is non-zero. Once we know that it's 4 mod 8. Okay. So all right. So I suppose and also I think I should be, I mean, the determinant of 2 times b is congruent to 4 mod 8. That's what we have from this equation here. But on the other hand, okay, so are we comfortable with moving on and looking at the other arm of the contradiction, where we will try to show that the rank of this matrix is in fact 2 and not 3? All right, thank you. Okay, so this matrix can be thought of as the product of these two matrices. And we know, and we have seen this also in, I think, recently, I think we used it in probably miniature number 4. The rank of a product is bounded by the rank of the matrices that contribute to the product. And here we are looking at a 2 by 3 and a 3 by 2 matrix. Well, okay, the first matrix is 3 by 2, the other one is 2 by 3. So both of those matrices have ranks bounded by 2, right? So this product matrix cannot have rank more than 2 for that reason. So that part of the argument was really quick, right? And I think it's just a matter of validating that these terms tally up as you would expect. But I think you can probably see that these diagonal entries are generated as just exactly as you would expect them to be. And if you pick up, for example, CB here, this is the third row, second column. So you look at the third row and the second column, sure enough, that is C1, C2, B1, B2. And that's, well, I don't know. I mean, that's essentially, I mean, this side of the argument is probably cleaner to just say that the rank of the matrix falls short of 3. On the other hand, what you have on the what you have coming from the fact that these were all supposed to be odd squares is the fact that these numbers here give you non-zero determinant. So that's a very, I don't know, it's sort of an implicit contradiction. And to be very honest, I don't know what to make of it. But also, I guess, yeah, in terms of notation, I don't think the miniature is explicit about the coordinates. So I'm only going to, I mean, the A1, A2, B1, B2, C1, C2, the coordinates of the respective points. You dump them in this matrix and take the A transpose product to get these values. Does that add up and make sense? Okay, that's awesome. It's a bit of a, I don't know, I mean, it's a bit of an anticlimax. I mean, everything does work out in terms of mechanism. It's not clear. I think the geometry really does translate into these inner products, and the oddness of the distances is playing into the modular arithmetic component of the argument. So that much is clear, but there's really no intuition for how somebody would come up with a matrix like this. On the other hand, I think let me just spend a quick 2-3 minutes maybe talking about the other result that I started out with, where I said you cannot keep on packing points that have pairwise integer distances. And I think the argument for that, and I'll keep it at a high level, but link you to the Wikipedia page, which does have a nice step-by-step proof. And here, at least, the argument feels like a little more natural. So suppose you have a collection of points where all the pairwise distances happen to be integers. Pick your 3 favorite points from this set. So I happen to have picked a Pythagorean triplet here. It doesn't have to be. Pick any 3 points that you like from a collection that somebody has given you. And well, those 3 points are going to form a triangle. And now if you think about, well, any other point, let's say, let's look at any 4th point in this collection. By the triangle inequality, we know that its difference, the difference of the distances of this point X from A and B is constrained to be at most the distance between A and B. That's the triangle inequality. The standard form is probably to pull the BX to the other side. But, you know, hopefully that aspect of it is clear. Okay, so if you have a 4th point, then it must lie on this, let's see where I have this. Okay, so here. So this is the hyperbola that traces, you know, the locus of all the points, whose distance from, okay, whose difference of distances. So this hyperbola here basically says that this difference is whatever it is. I think in this case, it's 1, this is 0, this is 2, and this is 3. So notice that there are only 4 possible values for what this expression on the left-hand side can be. The difference between the distance of x from A and the distance of x from B is at most the distance between A and B. But notice that we are assuming that all pairwise distances are integers. So in particular, dAx is an integer and ddx is an integer. So their difference must also be an integer. And it's an integer and it's at most 3. So it's only the only possibilities are 0, 1, 2, and 3, right? And the same argument can be made on the other side for looking at x from the point of view of B and C. So that's going to be this hyperbola here, which basically, again, the difference between the distance from B to x and C to x can be at most 4, and it's an integer. So it's going to be, it's going to be, this is what controls this. So it's going to be 0, 1, 2, 3, or 4, one of those. So you can play around with these two hyperbolas. You know that the fourth point, like the next, I mean, any point x that claims to belong to this collection must belong to both of these hyperbolas. Is that fair? Can you give me a +1 if this is clear? We have only used the triangle inequality and the fact that all pairwise distances are integers. Okay, awesome. Now it turns out that two hyperbolas can apparently intersect at most 4 points. So essentially, I mean, this distance between AB is some integer, let's call that x. The distance between BC is some other integer, let's call that y. So you have x plus 1 hyperbolas that come from the AB constraint and y plus 1 hyperbolas that come from the BC constraint. And each of those pairs can give you only 4 possible intersections. So you look at 4 times x plus 1 times y plus 1. Those are the only possible places that any other point in this collection could be, right? And maybe not all of them are even feasible because their mutual pairwise distances may not be integral and so on. But just A, B, and B, C, their distances already constrain you to these many points. So if somebody gives you a selection of points, you can probably pick, I don't know, like a really small triangle, the smallest triangle that you can find in there. Whatever that triangle is, however large the smallest triangle is, it's still going to be some finite pair of distances, x and y. And that basically upper bounds the number of points that you can add to this collection. So basically any collection of points that claims to have the property that the pairwise distances are all integers. I don't care about order even here, just that they're integers. Any such collection of points must be finite. And in fact, you have a somewhat explicit bound in terms of 2 of your favorite pairwise distances from the collection. So pick any triangle and a pair of edges, and that gives you a bound on how many points you can have. So I haven't made the discussion post for today. I will do that shortly, and there I will link you to the Wikipedia page on the Erdős-Anning theorem, which is basically this claim. And it has a nice proof, which is basically along the lines that we just discussed, and also link to this little GeoGebra applet for whatever it's worth. So, okay. So on that note, I think that's all that I had to say for today. And I'm going to stop talking at this point, but if you have any questions or comments, this would be a great time to discuss, and then we can close off the stream and hang out for a bit after that. So to be honest, like I haven't used GeoGebra very much, so I don't know the difference. I mean, GeoGebra tells me that I can share a link to just this demonstration, and just as I did that, it seemed to disappear. So I don't think I'm logged in from here. But okay, yeah, so it seems to be so I just opened the GeoGebra app and typed in the equations that I needed to get the two hyperbolas. I think it's an interactive thing that I can share, so I should be able to do that. Yeah, it's yeah. So this is GeoGebra on the web. I haven't used. I didn't even know that there was a dedicated app, but this is just from the web browser. Yeah. Yeah, I should acknowledge Jay. I don't think he's on the call, but I got some expert GeoGebra help in terms of connecting the sliders to the things that I wanted to change. So really appreciate that from earlier today. Yeah. Oh, I see. Yeah, they have some terminology on the website that I didn't fully understand. Like I said, I'm not really a GeoGebra user, but they seem to have at least what I would think of as a web app. And yeah, so I didn't have to download or install anything. And it seems to give me the option to share this as a standalone applet. So I hope to be able to do that in due course. Also, I didn't know about the Erdős-Channing theorem before this. The way I found out about it was by asking ChatGPT if it can find me 4 points that have pairwise odd distances. And it said it cannot do that, but I might be interested in this other theorem instead. I thought that was kind of cute. And it did try its best for 4 pairwise even distances, but it wasn't able to discover the Pythagorean triplet trick. But anyway, so that's just some totally random trivia. So yes, Vinay, you were about to say something?
Yeah, so if we can go back to the old proof, no, I would probably, I mean, people I think started discussing GeoGebra, not the miniature itself. So I would have presented this slightly differently in the sense that, so this particular, the first part that you have shown, the fact that, AA transpose is actually, gives you this, something like a covariance matrix, right, essentially.
Right.
So that is, I mean, the fact that it is rank 2 is sort of clear. Okay?
Mhm.
And this AA transpose is something that you use in a lot of places. So if that was the first part,
Mhm.
then what it amounts to saying is that, but then if you tell me that all the distances happen to be odd integers,
Right.
I can demonstrate that that particular matrix should actually have rank 3.
Should have full rank. Yeah.
Yeah. So probably, and mod 8 is something that does come up in number theory. I mean, I remember in multiplicative number theory, there are at least about 2-3 proofs which actually, where in the classification you will end up doing a lot of mod 8. Yeah. So mod 8 is sort of something that people in multiplicative number theory, I think it's in their toolbox.
Right.
So
Right.
it is not a strange object per se.
Mhm. Yeah,
Yeah.
okay. It's not as weird as we make it out to be. Yeah, no, I think that's just lack of familiarity on our end. But yes, no, I think it is true that I should have probably presented this arm of the argument first with the AA transpose and saying that, well, now we are going to try and show full rank. And here it's a bit of a, yeah, it's an argument that's rooted in the congruences. There were suggestions of doing it other ways, and it would be nice to see if I mean I think anything that doesn't leverage the fact that these are odd squares is likely to fall short. So the only trouble I had with the suggestions in the chat was that it wasn't clear to me where the oddness of the distances was coming into play, whereas this argument evidently relies on it. So yeah, that's yeah, but I do think that transferring the burden to the determinant of this matrix of congruences was like a clever computational trick and something that would have totally not occurred to me unless somebody just shows it to you. So
Yeah, but I have a feeling that if you just multiply these things, right? A1 square plus A2 square and all these entries. And you know that A1 square plus A2 square is odd, and a lot of these things are odd, right?
Right.
So if you actually do the determinant, probably with some effort, I think you will land up with something, a contradiction which actually shows that the rank is
Right.
has to be 3 because all these numbers are odd and so on. So this, I would think the mod 8 is only it's just a cleaner version of
It's
MSE proof.
probably a cleaner or shorter way of doing. That's a good point. I think we could, I mean, it's a small matrix, so we could just work through the whole determinant expression and maybe observe that it's non-zero just from first, I mean, just from the fact that each of these individual things are odd. So that's yeah, that's a nice homework for tonight. I think it would be nice to just hash this out without this wizardry. Yeah.
I have to make this joke that you can expand the determinant, and given the oddity of all these things, you can figure out that it's full.
Yes, that's right. Well, one hopes indeed. All right. So thank you so much, Vinay, as always, and everyone else. So
there's a question there.
there's a question: if the product of these two matrices is the left matrix and the product matrix is rank at most 2, then how come it has rank at most 3? Yeah, so Manmohan, I think that's exactly the point. You cannot have a matrix whose rank is simultaneously 2 and 3. And so this whole thing was set up to be a proof by contradiction. So we started by assuming that there are 4 points where all the distances are odd. And then maybe like I should have, like when I was saying, I should have just shown you this matrix first, which we know is a rank 2 matrix. That part is evident. And then we go on to argue that it's also full rank. If it turns out that it's full rank if everything is odd, but that contradicts the fact that we know it to be a rank 2 matrix to begin with. So I hope that that's clear now. This, I mean, again, I should have emphasized it on the slides. Oh, okay. So I did have the determinant claim in writing. I just forgot that it was, I think the sequencing was off. I'm sorry, but you can still refer to it offline. Anyway, so the point is that this whole thing was set up to lead us to a contradiction, and that's the contradiction that we have at the end. And yeah, maybe to make it look a little less sort of out of the blue, I think, yeah, setting up this matrix is still, I think, a clever step, but maybe just working through the determinant, observing that it's non-zero, I think that's doable without the funkiness of the 1 mod 3. But now that you know the funkiness of 1 mod 8, but now that you know it, it's probably a toolkit to add to your it's a tool to add to your toolkit. Yeah. So all right. So on that note, I think this is probably a good place to stop. Tomorrow's miniature is also another one with a geometric flavor. And it's also again about distances, but there is no parity business as far as I remember.
Did Manmohan understand? We didn't check.
Oh, right. Yeah, sorry, Manmohan. I hope that was clear. Yeah, all right. Thank you very much. All right, then. Thanks everyone for joining. I think the slides could have been a little bit clearer today, but hopefully it still made sense overall. And tomorrow, more distances and more fun. So see